Stefan Heimersheim's talk on Cannibal dark matter. So with that, I would like to give him the floor.
Yeah, so I want to use my 4 minutes to talk about cannibals. That's based on a project I submitted a few weeks ago together with Niels, Diana, and Julian. And cannibals is basically a name for a class of dark matter particles that have number-changing interactions. In particular, 3 to 2 interactions. So where 3 particles interact, they cannibalize one of them, and the mass energy gets converted to heat, and you get 2 particles remaining. And you might have heard this name already in Pranja's talk, also about cannibal dark matter, although our models were different, and we have different results at the end. So basically, you just have some dark matter particle that does have a mass somewhere in the kilo electron volt to mega electron volt range, and we don't assume any interactions with standard models, so it's a secluded dark matter. And this leads to an interesting temperature evolution. So in the beginning, you just like any particle, it behaves like radiation, where the temperature is much higher than the mass. But as soon as it gets non-relativistic, so that's this point, the green region in the plot, where the red line is the temperature over the mass. So that you see that the temperature then gets constant. And this is because this 3 to 2 interaction is actually relevant, and all this mass that gets converted to energy keeps the temperature almost constant. So it goes like 1 over log A. And this continues until the interaction freezes out, so until the interaction rate is low enough, and then just behaves like cold dark matter because you don't have these interactions anymore. And what we did is implement this model into the Boltzmann solver class and look what effect it has on the cosmic microwave background and on the matter power spectrum. And what I want to show you here is the matter power spectrum. So what I have plotted here is the Cannibal's matter power spectrum divided by the matter power spectrum that you would get for lambdas dm. And what you see on the large scale, so on the left side, is the ratio is 1, so there's no change. It's just the same spectrum. But on small scales, on the right side, you see that you get a suppression. And this suppression depends on how much of dark matter is actually cannibalistic. So we just say we have some fraction of dark matter that can be cannibalistic. It can be everything. It can also be only a part. And you get the step in the power spectrum that depends on the interaction strength. So the stronger the interaction, the larger the scales that you suppress. And this, of course, has interesting, so it looks pretty much similar to warm or even hot dark matter. So we get similar suppression, but as opposed to these models, it's actually compatible with CMB, while you get a nice suppression. So what I'll show you here is our MCMC results from using CMB and BAO constraints. And what you see on the y-axis here is the fraction of matter that's cannibalistic of dark matter. So at the top is 1 and the bottom is 10 to the minus 2. And on the x-axis, the interaction strength, from very weak on the left to strong on the right. And all the points are basically the allowed parameter space. And you see, of course, on the left, you just have a really low interaction strength. So the freeze out is very early. And basically, for all intents and purposes, you just have cold dark matter. But on the right, you have a strong interaction, and the cannibalistic phase goes until today. And that's, of course, excluded. And the thing I want to point out is the color. So that's the S8 value. And you can see that close to the boundary of the allowed region, you get a really low S8 value, actually close to the value that's preferred by the weak lensing measurements. And that's still allowed, like only slightly is still allowed by the CMB. And the effect why these two boundaries are so close together is basically that the S8 value, for the S8, you need the suppression to be on large scales enough that you affect S8. So if you have the interaction rate too weak, the suppression is on very small scales and you wouldn't notice that. While for the CMB, you need the freeze out to be late enough. And these two effects counteract each other, which is why you have only this part in the middle where you get actually a low sigma 8 compatible with CMB. But you can get this. So you get a slightly worse CMB fit, but you can get value. So that's the take home message. With Cannibals, you can get S8 down to 0.7. Okay.
Great, thanks for your talk, Stefan. So if there is more discussion, like if there are any questions, then I encourage everyone to take up the discussion on Slack Epsicoco later.
Yeah.
And with that, I would like to give the floor to Bart Horn. Bart, can you share your screen?
Will do. Is the sound okay?
Yes.
All right, here we go. Okay, hello everyone. I'm Bart Horn from Manhattan College. I'd like to thank the organizers for an excellent conference and for the opportunity to tell you a little bit about observable relics from the simple harmonic universe, which is a paper that I put out recently with my student Peter Gilmartin, also based on some previous work on the simple harmonic universe with Graham, Khashru, Rajendran, and Toraba. So the simple harmonic universe is a model that we originally considered in the context of thinking about singularity theorems. You can avoid the Big Bang singularity in the past if you violate the null energy condition with flat or open spatial slices, or violating the strong energy condition if you have closed spatial slices. So this specific model consists of closed or spherical spatial curvature, which makes a negative contribution to the Friedmann equation, a negative cosmological constant, and an exotic matter source with an intermediate equation of state between those two. And if you plug these all into the Friedmann equation, you can get a scale factor that is periodic within the context of general relativity and null energy condition preserving sources. We showed in an earlier paper that this universe can be made stable at the level of linearized perturbations as long as the sound speed is positive. And lately we've been thinking about what can happen if this tunnels or evolves into the present epoch. In particular, it suggests a number of slightly unusual search templates, in particular positive curvature, which is somewhat less favored in the theoretical literature than negative curvature is. This may or may not be accompanied by a string-like matter source that energetically cancels curvature out of the Friedmann equation. And another signature that we looked for is a modified dark energy sector consisting of a cosmological constant that is negative today, as well as, and that's over-canceled by a dark fluid with W slightly greater than -1. So you can have a recollapsing dark energy sector. We've searched for all these things using class and Monty Python and various data sets. Unsurprisingly, what we have are constraints and not discoveries. But what the constraints look like, positive curvature is constrained at about the % level. Using the Planck data alone, there's a mild preference for a closed slicing, which has been discussed in a few recent works. But if you add BAO data to that, the error bars are still consistent with 0. It's also possible that positive curvature can suppress the primordial quadrupole, essentially because the universe is too large for that mode. And we have some ideas in model building on how that can be made consistent with the non-detection of curvature using the position of the CMB peaks. Adding string-like matter changes the constraints on the curvature parameter only very slightly, but this is still going to be important for the next generation of experiments looking for curvature. And finally, the constraints on the modified dark energy sector can be transformed into a bound on the lifetime of the universe. And the experimental constraints imply the recollapse time is greater than at least about 30 Hubble times. So I'll stop there. Thank you very much. And I'm happy to discuss more either by email or in the Slack chat if anyone has questions. Thank you.
All right. Thank you very much, Bart, for the very interesting talk. With that, I would like to now hand the floor to Keir Rogers. Keir, are you there?
Yes.
Yeah.
Okay, can you all see that?
Yes.
Okay, great. Okay, so hi everyone, Keir Rogers, postdoc in Stockholm University. And I'm pleased to have a few minutes to tell you about a new project that we put out in the archive, got the archive numbers at the bottom there. looking to put bounds on the mass of ultralight axions as the dark matter using the Lyman-alpha forest as a trace of the large-scale structure. So, because don't have that much time, I'm going to rely on René's talk, who motivated well why we should consider ultralight axions as dark matter candidates. I just have bullet points there to kind of summarize the main things, which is that an axion was initially evoked to solve the strong CP problem, was realized it could be a dark matter candidate, and since then a wider class of what are called axion-like particles have been invoked with motivations from string theory, and also from possible solutions to possible tensions in what's called the small-scale crisis of cold dark matter, or other baryonic avenues are viable solutions to that. And from both the string axiverse, where there might be a preferred mass scale, and also from the small-scale crisis, there's what I will refer to as a canonical mass scale of about 10 to the minus 22 electron volts. And this then, because this axion particle was so light, has wave-like phenomena on astrophysical scales. And so the primary feature in the power spectrum, which then is the plot on the right, is this cutoff in the power spectrum. So this is the square root of the ratio of the power spectrum of the dark matters ULAs over the cold dark matter limit. And you see that you have this cutoff in the power spectrum below a certain scale, which is set by what's called the quantum pressure. And that the scale of this cutoff is a function of the mass of the axion, with the scaling given here, such that heavier axions have wave-like features on smaller scales, and so at higher K you see the cutoff. And so what we're going to do is we're going to use the Lyman-alpha forest, which is a spectroscopic feature, absorption feature in the spectra of high redshift quasars that traces fluctuations in the intergalactic medium. And because the intergalactic medium is basically at mean cosmic density, there's very little nonlinear evolution. So this is a trace of linear perturbations in linear power spectrum at high redshift where these quasars are observed. And if you have very high resolution spectra, you start to probe very small scale density perturbations. And so by having high resolution data, which new data sets have recently been released, you're able to look for cutoffs from heavier axions and push the lower limit on allowed axion masses to higher values. Now, the challenge in this analysis is that because these Lyman-alpha forest fluctuations are being sourced from intergalactic medium, you need to marginalize robustly over uncertainty in the state of the intergalactic medium, its temperature, how that's distributed, and how ionized it is.
All right. Yeah, thank you. Thank you very much for the flash talk. With that being said, you unshare your screen, then we can now then I would like to hand the floor to Trivedi. Actually, sorry. This the first one is Urena-Lopez.
Thanks.
So if you can share your screen, then we can proceed.
Okay, can you see my presentation now?
Yes.
Excellent. Hi, everyone. I want to thank the organizer for this opportunity. My name is Urena-Lopez from University of Guanajuato in Mexico. I'm going to talk about these ultralight scalar fields, story of three potentials. This work has been done in collaboration with Professor Tonatio Matos, Dr. Alma Gonzalez Morales, Stefan Medellin, and Francisco Linares. So you have heard just recently from these ultralight bosons to explain the nature of dark matter, but 20 years ago, this idea came up for the first time. And in this slide, you can see this famous fuzzy dark matter paper. They were thinking about the non-relativistic properties of ultralight particles, but there were other ideas around in which we were considering the relativistic part of this model. and we were solving the Klein-Gordon equation for the cosmology. The simplest potential is the quadratic one, which is the fuzzy dark matter case. But I'm going to show you other possibilities which are probably more interesting. The first one is the Axion-like potential. You can see here that the functional form of the potential is trigonometric cosine. And there is an extra parameter here, which is the Axion decay constant, this FA. But for the cosmology, the important parameter is this lambda that you can see here, which is a combination of the Planck mass with this Axion decay constant. The fuzzy dark matter case is recovered for lambda equals to 0, which means that the Axion decay constant goes to infinity. Like in the case of fuzzy dark matter, there is a suppression in the mass power spectrum, the linear mass power spectrum, that you see in the plot on the lower left. But there is in addition a bump in this mass power spectrum, an excess of power with respect to cold dark matter, which is because of the presence of this extra parameter. So this extra parameter can help the model, can help fuzzy dark matter.
Louis, if I may very briefly interrupt, are you going through your slides at the moment? Because we can only see the title slide.
Ah, sorry. Yeah. I'm sorry about this. I'm going to, let me try again. Yes, I'm sorry about this. Can you see my slides?
Yes.
Slides? Sorry about that. So I was talking about this Axion-like potential. This parameter, this extra parameter in the potential can help the fuzzy dark matter to be more consistent with constraints coming from Lyman-alpha observations, for instance. We have shown that in recent papers and also other people in other groups. So I'm going for the other case, which is the Koch-like potential. This time we have this hyperbolic cosine. Again, there is an extra parameter here. And as before, for the Axion-like potential, there is this combination for this parameter lambda between the parameter and the Planck mass. This time, there is a suppression of power, which is quite similar to the case of fuzzy dark matter, and there is no excess of power in the linear mass power spectrum. So there is no difference between fuzzy dark matter and the Koch-like potential. In addition, this Koch-like potential is going to contribute as an extra relativistic degree of freedom at early times, but if the mass of the boson is large enough, everything is consistent with constraints coming from Planck observations. And this suppression of power in the mass power spectrum was shown for the first time in a paper of ours 20 years ago, but has been confirmed in other works. If you go to the non-relativistic dynamics, this extra parameter, this lambda parameter, is going to show up as a quartic self-interaction in the Schrodinger equation, in the Schrodinger-Poisson system of equations. And this has consequences for the critical mass of gravitational collapse of these kind of models. I'm not going into the details, but probably you can take a look at this slide after the talk. So I'm finishing here. There are current constraints on the boson mass for these ultralight particles. You can see some of the most recent constraints on this mass. The question is, where is the parameter lambda? Where is any other parameters in the model? These constraints only work for the boson mass, for the fuzzy dark matter case, but probably there is something else if we consider an extra parameter in the potential. And that's it. Thank you for your attention.
Thank you for the very interesting flash talk. Then we can move on to now Trivedi.
So like firstly, is my slide visible? Like, is my voice audible? Yeah. Okay. Yeah. So firstly, I would like to thank the organizers once again for giving me this opportunity. So today I will be telling a bit about my work on the Swampland conjectures and single field inflation. So like it has been a famous problem in recent years that the Swampland conjectures have been shown to be a bit um, inconsistent with single field inflation or vice versa. It depends on you. Um, if it is the de Sitter conjecture or the distance conjecture or the newly proposed TCC, all of them induce either fine-tuning or severe disagreements with single-field inflation. But multi-field models of inflation or the likes of worm inflation, even for the single-field case, have been shown to be quite consistent with the conjectures in certain limits. So it's not all hope dead for the conjectures and inflation. And it has also been shown that in some general cosmological scenarios like chaotic inflation, in the brain world scenario, the single field inflation can be in good agreement with the conjectures. So I used the exact solution approach to inflation. So the exact solution approach to inflation is a very powerful method to study inflation in a range of different cosmologies. The generalized Friedman equation in this case is the follows, and this equation is quite general because one can study a range of cosmologies using this, the Chern-Simons cosmology or brain world cosmology, even LQC. So the equation is quite general, and the epsilon and the epsilon and eta parameters for this scenario, in the case that there is single field inflation, are the follows alongside the scalar spectral index. And obviously one can further consider more perturbative analysis of the same. Now, the central points of conflict between the conjectures and single field inflation is that basically the distance conjecture constrains the field space for which any EFT will be applicable, and the de Sitter and the refined de Sitter conjecture set constraints on the potentials. So one central point of conflict, which is observable, is that the de Sitter conjecture is in stark agreement with the condition of the epsilon Scalar parameter being very less than 1. This is epsilon in the GR-based cosmology. Another issue is that there would not be sufficient number of E-folds as del phi is equal to V prime by V in the very approximate case. So obviously for the conjectures it will be less than 1, which is something which we would not need, and they would and the definitions of the conjecture are not consistent with the data on single field inflation in GR based case. And now if we apply the exact solution approach on inflation and try to study inflation in general cosmologies which are allowed by the approach, we see that it is only the f equal to h square case, which is for GR, that there are stark problems with the conjectures. As you can see, that v prime by v can be greater than 1, and still we can have epsilon which to be less than 1. In the GR case, we get this relation between the spectral index and the conjecture parameters, which leads to lower orders of the conjecture parameters from their string theoretic definitions. But in general cosmologies, we get this relation, and again, it is only for f equal to h squared that we are having stark conflicts. The string theoretic definitions of the parameters can be made consistent, and we can still have appropriate values of the spectral index. And finally, we can also have enough amount of inflation, as one can see that we can fine tune the free parameters of the model, not the physical quantities like the energy scale or stuff like that. We can fine tune the free parameters of the model and can have enough amount of inflation as well. So I would like to end here, and basically the conclusion of this whole thing is that in general cosmological scenarios, inflation, single field inflation and the Swampland conjectures are not in unavoidable conflicts with each other.
All right, thank you for the very interesting flash talk. Then the last speaker on the list is Benjamin Giblin.
Hi, I'm Benjamin Giblin, a postdoc at the University of Edinburgh. In this flash talk, I'm going to be discussing KIDS 1000, the latest data release from the Kilo Degree Survey. KIDS 1000 is a catalogue of redshifts and galaxy shape distortions, or Shear, measured from 21 million galaxies. These galaxies span 1006 square degrees on the sky. You can see the footprint of the survey depicted above the VLT survey telescope here. This is the telescope used to observe these images. KIDS 1000 was recently discussed in a bunch of papers on the archive, but in this flash talk I'm focusing on work in my own paper, Giblin et al., in which we performed the robustness tests of the Shear and Redshift calibrations. More specifically, I'm going to focus on the PSF modeling. There's many ways in which errors in the PSF modeling can lead to bias on your constraints on cosmological parameters. The biases might come from mismeasurement of the PSF shape and size. It could come from imperfect deconvolution of the PSF from your imaging. The way in which you choose the objects for your PSF modeling and the noise in the imaging of those objects can be problematic. But the effect that we found to be most significant comes from instrumental defects. This can give rise to a flux dependence in your PSF modeling errors that can vary from CCD to CCD in your camera. Here I'm showing a 1 square degree image in the R band taken by our telescope. There are 2 CCDs that are highlighted by the red squares that we found to have particularly strong flux dependence in the PSF modeling errors. So we propagated those PSF modeling errors into a bias on the measurement we use to constrain cosmological parameters. That measurement is a shear correlation function. It's basically a measure of how correlated the galaxy shapes are as a function of their angular separation. Here I'm showing you the biases on that measurement that arise from different sources of imperfect PSF modeling. And the bias that arises from flux dependence in the PSF modeling errors is the magenta term, the one that we find to be most significant in terms of its impact on your cosmological parameter constraints. Fortunately, in the case of this data, the PSF model is sufficiently accurately constrained such that this flux dependent bias is still quite small. It induces less than a 0.1 sigma change in our constraints on the clustering parameter S8. So it's fairly benign for KIDS 1000. However, this is definitely something that should be tested and modeled with future upcoming surveys like LSST and Euclid, because typically looking at flux dependence in your PSF modeling is not part of the standard tests for validating your PSF modeling. So that's pretty much the takeaway message. If you have any further questions on KIDS 1000 or weak lensing cosmology in general, please don't hesitate to get in touch with me. Thank you.